For my project, I studied whether optomechanical sensing would be a viable technique to search for dark matter in boson stars. So, as of now, there is significant astronomical evidence for the existence of dark matter, though no specific particle has been detected yet. In recent years, focus on dark matter research has shifted to ultralight dark matter candidates such as axion-like particles, since heavier candidates have not yet been detected. One particular detection technique which could search for ultralight dark matter candidates is optomechanical sensing. Essentially, optomechanical sensing is when you have a mechanical force sensor suspended from a pendulum coupled to an interferometer. When dark matter hits the sensor, it causes a change in the fundamental frequency of an optical cavity, leading to a phase shift in the interferometer, as you can see in the picture here. Previous works have shown that this type of detector offers many advantages, especially when scaled into an array. We assume that ALPs interact with the standard model via a Yukawa coupling to neutrons, which has the effect of modulating the mass of a particle. As a boson star moves across the sensor, the center of mass of the sensor shifts towards the boson star's center of mass, causing the sensor to move. Formally, we assume that coupling is of the form shown here, where y is a coupling constant. And we assume that the dark matter field is of the form shown here. Since the Gross-Pitatsky equation describing the star is Galilean invariant, the field psi gal must obey this transformation law. And then combining the two above equations, this implies that the dark matter field must be of the form shown here. And then by noticing that the coupling term behaves like a mass term in the Dirac-Lagrangian, we determine that the force on the sensor due to an ALP boson star is of the form shown here. So now to model the boson stars, we assume that they're described by an energy functional of the form shown here, where Vg is a gravitational potential and lambda is the self-interaction between the bosons. To determine the wave function, we use a variational technique with a variational ansatz of the form shown here. Now we minimize the energy functional with respect to sigma d and obtain the following value for sigma d. Substituting this back into this variational ansatz gives us a very good approximation for the wave function of the boson star. Once we have an approximation of the wave function, we can evaluate the central density, which is of the form shown here. Now, to verify that this estimate for dark matter density is consistent with observational results, we compare the density of the boson star with observational upper limits on the matter density in our solar system at different points from the sun given in a paper by Pitijeva et al. And then we can determine that the upper limit on boson star density at the Earth is approximately equal to 10 to the negative 19th grams per centimeter cubed. Compared to a diffuse dark matter field, which has density approximately equal to 10 to the negative 28th grams per centimeter cubed, a boson star centered around the sun has a much higher density. This leads us to hypothesize that the signal we could expect to observe would be much higher since signal scales in proportion to the square root of the dark matter density. So now to determine the collision rate for boson stars outside of our solar system, we assume that the collision cross-section is of the form shown here, where our target is approximately equal to the Earth's radius and R99 is equal to the radius in which 99% of the mass of the boson star is contained. We assume that mean free path is of the form shown here and number density is of the form shown here. Then we can determine that the frequency is equal to this value shown here. Now, if we rewrite the frequency in terms of the central density, we can obtain this equation here. So one constraint on the allowable coupling values comes from Big Bang nucleosynthesis, which is essentially a calculation which predicts the abundance of helium relative to hydrogen to a very high degree of accuracy. So in this calculation, we assume that the neutron to proton ratio is equal to this equation here, where Q is the neutron proton mass difference, and then the change in neutron proton mass difference due to ALP coupling to the standard model is equal to this equation shown here. So the mass fraction of helium is given by this equation here, and then the change in mass fraction due to and ALP would be equal to this equation shown here. Since helium abundance is known within 10% accuracy, delta YP over YP is less than 0.1, and then we can solve this algebraically and get a numerical constraint on coupling in terms of the mass of an ALP. So now we must also look at constraints from fifth force experiments. So essentially, if we were to introduce an additional particle to the standard model, it would induce a fifth force, which we have not yet detected. And so what we found is that these experiments place the tightest constraints on ALP coupling to the standard model. Essentially, if you compare fifth force constraints to constraints from BBN, we find that fifth force experiments place a tighter constraint on coupling than BBN across the parameter space. So, in conclusion, we think that boson stars have a higher we found that since boson stars have a higher density compared to a diffuse field, optomechanical sensing could be sensitive to ALPs in boson stars centered around the sun and boson stars in outer space. To finalize the calculations of this project, we still need to determine the possible signal we could expect and finish scanning over the available parameter space to determine detection reach.